Alright, so in this lecture I mainly want to look at using the C mode of the cells in the simulator, but first of all, a quick comment. If you use a single dash help when you invoke the Java simulator, that will give you the usage information that I was trying to do in a previous talk. So dash help gives you the commands. Dash dark says run without displaying any graphical outputs, so you can use that like if you're running on a headless server, for example. Dash size, you can put in number of rows, x number of columns, and that will give you a matrix of a particular size, or you can also add a third number and that will give you a three-dimensional matrix which you can interact with. Dash client tells it that you want to run in a client server mode, and add a init file will just let you execute a series of initial commands from a init file when it first starts loading the simulator, and then it will come back to a command prompt. So I'm going to bring in my graphical window here, and I want to look at playing with the C mode inputs, the C mode of cells using the C inputs. So remember, if I dump out the truth table for cell 00, it's all zeros initially. And if I set cell 00 control west to 1 and set cell 00 data west to 1, the truth table itself doesn't change right now, but if I do a single clock tick and I dump out the truth table, you'll notice there's a single 1 that's been shifted in. This is the first bit that gets written when a cell goes into C mode. If I tick a second time and I dump 00, there's 2 bits. We just wrote this second bit into the truth table. Now if I set 00 data west to 0 and I tick a third time, we've actually just written this 0, which was already in our table, so we haven't noticed it. But now if I set 00 data west to a 1 and I tick a fourth time and dump 00, we see that we've written our fourth one into this fourth position. So by turning the data west input on and off at the right times relative to the clock ticks, we can load bits into these output values in the truth table, beginning at this bit, moving across each row in sort of a negative column major through all the D outputs, and then starting over here in the C outputs and going backwards. So if I tick another 60 times, I'll fill up this entire set with 1s except for that 1 bit that I missed. And now if I tick one more time, we'll begin filling in the C columns from this 15th row leftmost column, and we'll move through there. If I tick another 62 times, we've now filled up everything except for this last bit. This is the 128th bit. If we tick once more and we look at cell 00, we filled it up with 1s, and the next bit we're going to write is this bit again here, the first bit that we wrote before. So if I set 00 data west to 0 at this point and I tick and I look at 00, well, there's a 0. So we're continually rewriting this truth table as long as the cell stays in C mode. Now if I take the cell out of C mode, set 00 control west 0, you notice the input arrow is no longer red, but we're seeing red on the output of all 4 sides of this cell. This is because this cell, it has 1s in almost all of its positions. In fact, if we look at the Boolean equations, we basically see control north, south, west, and east are equal to 1. Data north and south are 1. East and west have these slightly more complex expressions corresponding to these zeros. But this cell is now trying to program the cells to its west and north, east, and south. These are, of course, edge locations, so there's no cell there. So, and that's an interesting configuration we'll talk about when we discuss guard cells and guard walls and guard rings. But anyway, that's the basic C mode interaction. Now let's reinitialize to get rid of that. And again, we can dump 00, and it's just 0. So if we were to toggle the data west input at the right times, we could load some interesting truth table into here. For example, if we wanted to take data from the west and send it to the east, what we would want to do is in these first 8 rows, we would want to leave data east equal to 0, and the next 8 rows, we would want to leave data east equal to 1. So we would set data west to be 0010, 0010. In other words, we would turn it on every 4th clock tick for the first 32 clock ticks, and then we would leave it off and we could take the cell out of C mode. That's a hard thing to do by hand, so there's a shorthand that we can use. There's a truth table we can compile into in memory. If we just say D, it just shows us what the truth table is in this memory location. If we say B, it shows us the Boolean equations. And if we want to compile, we can just say C, and it will compile truth tables into memory, or equations into memory. So I can say, for example, data east equals west. And now I've compiled a truth table for this equation, but it hasn't been loaded into any particular cell. It's just being held in this imaginary cell, this memory location. I can say dump to just see what that value is, and there we can just see the bit values corresponding to it. There's our 8 ones, everything else is zeros. Now if I want to shift this bit pattern into this cell on the next set of clock ticks, there's a command for that. I can say set 00 data west from memory, and this will do two things. One, it will take the bits starting with this first bit of the truth table, and it will use that to drive the data input on this side, the data west input in this case. And two, after it applies this bit, it will tick the clock. And then it will apply this bit and tick the clock, apply this bit and tick the clock, and so on. And it will do that 128 times. So if I say set 00 data west M, we might be able to see a quick flash up here as it's loading that in, but probably not. That was pretty quick. And you notice we've had 128 clock ticks transpire and some number of events and propagation delays, but nothing has happened. This cell's truth table is still empty because we did not put the cell in C mode. But now if I say set 00 control west to a 1, and I feed the data west from memory and say tick the clock 128 times, the cell turns blue, indicating that there's some non-zero bits in there. And if we look at its truth table, it's actually got this combination that corresponds to the equation data east equals west. Now, if I set data west to be a 1, it does not propagate through because the cell is in C mode. And in C mode, all the D outputs on the non-active sides are driven to 0. But if we turn off that C input, set the control west to 0, it begins acting according to its truth table, in this case taking the value from the west and sending it to the east. And if I set data west to 0, then the output goes to 0. If I set it back to 1, the output goes to 1. Incidentally, there's another command we can use if we're trying to stay away from the graphics for some reason. We can use the output command. We can say output 00, and we get a display of what the D and C outputs are for the cell. In this case, data east is a 1. If I set data west into a 0 and I say output 00, we see that data east out has gone to a 0. So that's just a useful mnemonic that we can use for analyzing the outputs of cells without having to look at the window graphically. So this is going to lead us to the notion of sequences, which will be the 5th lecture in this series. But first we're going to talk about in the next lecture some example circuits that involve using the clock, and will give us a better idea of how to interact with the clock in a free running setup.